Hello everyone, welcome to the new lecture series. In this lecture series, we'll be talking about the concepts of efflux, that is the topic of fluid mechanics. Now this topic is not only important for the JEE advanced aspirants, but it is also important for the students of mechanical engineering or civil engineering who are appearing for GATE mechanical or GATE civil. So let's study this topic. So efflux is basically the outflow of a liquid through a orifice or through a hole. Now the first concept we learn is what is the velocity of the outflow of a liquid which is having a hole at depth h from the surface level. It can be considered as a projectile motion which is falling vertically downward. If it covers height of h having initial velocity 0, what is the velocity after it covers height h? We know that is equal to v equal to root over of 2gh when it comes to this height. Now, if a hole is there at depth h from the surface, fluid or the liquid flow will come with velocity of root 2gh only. Same. Now the projectile motion concept I just told to explain in a easy way. Now the actual concept will lie in the Bernoulli's theorem. So we'll try to prove this v equal to root over of 2gh, that is the velocity of efflux when a hole is there at a depth of h from the surface, that is the velocity of the liquid coming out from that hole. Now see, Bernoulli's theorem is nothing but the conservation of energy. So at this height, what is the pressure energy? So this is one point we will consider, that is the topmost point, and this is the point we will consider when the liquid is getting out from the hole or through the orifice. So at point 1, the pressure energy is P atm plus there is potential energy also. So we will try to consider the mass per unit volume is how much, that is the density, nothing but the density. So here this is the pressure energy. The next energy will come, that is the potential energy. The potential energy per unit volume is nothing but rho into G into H, because we are taking the reference level at point 2. So here we will consider that potential to be 0, U to be 0, plus the kinetic energy. But here the surface level liquid is not moving with any velocity, so we will consider the kinetic energy to be 0, that is the Ke to be 0. Now on the same streamline, if this liquid is coming to point 2, it is going out through the hole, that time suppose its velocity is v. Now that time also we will write the energy conservation. So what is the energy? See, it is open to the atmosphere, so the pressure will also be P atm, plus we are considering at this point the potential to be 0, so we will consider potential energy to be 0, plus kinetic energy per unit volume is half of rho into v square, because rho is the mass per unit volume. So per unit volume the energy is half of rho into v square. V is the velocity of the efflux, so that will be equal to this one. So we will write down this one, because we will consider that there is no loss of energy, rho gh. Now see, P atm will cancel, so half of rho v square, that will be equal to rho into G into H. So rho will also cancel both the sides, so V will get as root over of 2gh. That is the actual proof of the velocity of efflux. This is just for an easy demonstration, and if you go into the depth, you have to apply the Bernoulli's theorem at the surface level point liquid and at the point where it is emerging out through the hole. Now we will go to another concept. Now the velocity of efflux is well known, that is root over of 2gh. Now we will go to the another concept. Now we will discuss about the horizontal range of the liquid coming out. Now we will again draw one container which is having orifice here at the depth of h from the surface of the liquid. Now what is the velocity of efflux? At depth h, the velocity is root over of 2 into g into h. Now the horizontal range means at what point from this bottom point of the beaker the liquid will hit the ground. So horizontal range you have to find out. So this is nothing but a projectile motion we can consider, because this will emerge with the horizontal velocity of root over of 2gh. Now if the depth is h, I have to also tell what is the total liquid height h. Now see, if the depth of the hole is h, what is the remaining height? H minus h. Now this problem will be reduced to a problem of projectile motion from a height. Now we will draw the similar diagram here, where a projectile is projected with velocity of root over of 2gh from a height of h minus h. So it is a projectile motion problem we can consider, projectile motion from a height. Now the velocity of projection is root over of 2gh. Let's say it is taking time t to reach the ground at this level. Time t. What do you know from the projectile motion from a height? That this horizontal velocity will be constant throughout the motion. So this range, let's say it is r. R will be covered by the horizontal component of the velocity only, that is root over of 2gh only, 2gh into t. That is basically ux into t is basically range r. Now the time required to cover this height is how much? H minus h, that is the height of the projectile right now. That will be covered, that will be under the gravitational field g. So there is no vertically downward component of velocity initially. So 0 plus half of gt square will write. So what is the time taken to come to this point for the liquid? T is equal to root over of 2 into h minus h by g. Now we will put that time in the equation number 1, that is the range equation. If we put that, the range we will get as root over of 2gh into time is already we got, that is 2 of h minus h by g. So see, this root g will cancel, 2 will come out of the root and it will be root over of h into h minus h. So range is becoming r is equal to 2 into root over of small h into capital H minus small h, where this small h is the depth of the hole from the surface and capital H is the entire liquid height h. I hope it is clear. Then we will proceed to the next topic. Now the next topic is, what is the condition for having the maximum horizontal range? That means where should I keep the orifice or the hole from the surface level of the water or the liquid so that I can get the maximum range. That means at the maximum distance this liquid will touch the ground. So for a particular container, the level of the liquid or the height of the liquid is constant, that is capital H is constant for a particular container. Now keeping that constant, where can I make the hole or the orifice from the surface so that I can get the maximum range? Now see, the range is given as 2 into root over of small h into capital H minus small h. So I have to find out the value of the small h so that I can get R maximum. So R maximum means R square also will be maximum. So R square is 4 into h minus h. Now this is a find out the maximum problem. So maximum I have to find out for the R square also with respect to small h, because capital H for a particular container, as I told, is constant. So h is the only variable. I can vary the depth of this hole. Here also I can make, here also I can make. So multiplication rule, 1 into h minus h plus h into differentiating this term, that is minus 1. So that will be equal to 0, that is the condition for the finding out the maximum. So h minus 2h, that is equal to 0. So value of h is becoming capital H by 2. So I have to make a hole or the orifice at half of the total height so that I can get the maximum range of the liquid coming out. So that means I have to make just at the middle, I have to make the hole in order to get the maximum range here, so that it is max. And what is the value of this maximum? I'll just put h equal to h by 2 in the range equation and I'll get the maximum value of the range. So r, I'll put in the equation of r root over of h by 2 into h by 2, that is h. So range maximum is h only, that we got. Now we'll go to another small topic. So we got that at the middle point, if we make a hole or the orifice, we'll get the maximum range. That means the liquid will hit at the maximum distance from the beaker point. Now see, if I make a hole at depth 0, that means if I keep h equal to 0, we'll get range equal to 0 also. Now again, if I make a hole just at the bottom, so if the value of depth of the hole I keep as capital H only, then also I'll get range equal to 0. So see, range is maximum at the middle and the range is 0 in the either direction. If I make hole here, then also range is 0. If I make hole here, then also range is 0. So range is varying from the maximum to the minimum to either side of the hole. So I can find two such points if I make a hole at the top of the middle height and I can make a hole at the bottom of the middle height. For both of this height or both of this depth, I'll get the same range. Now there is a very easy trick to find out those 2 points where I'll get the same range. Closely observe this range equation. The range is 2 into root over of small h into capital H minus small h. So that is a hole if I keep at height h from the surface, I'll get this range. Now if I make a hole at the depth of h minus h, what will be the range? Let us find out. Range will be that time 2 into root over of h minus h into h minus of h minus h, that is root over of capital H minus small h into again this h. So if I make a hole at a depth of h from the top and if I make a hole again at a depth of h minus h, I'll get the same range. So h minus h depth also I'll get the same range and h depth also I'll get the same horizontal range like this. It will go like this. I hope till this point it is clear. We'll meet on the next video. Thank you so much.